So we're going to start the faculty panel. I have, I think, a great panel here. I forgot the intros last year, so I will make sure to introduce everyone this time. Starting on the other side, we have Professor Shriram Krishnamurthi, who is a professor of computer science at Brown University. His research vision revolves around answering the question, how do we help people effectively learn about abstractions? And currently, he mainly works on Pirate and devotes a substantial portion of his time and energy to computing education research. Next, we have Stephen Holtzen, who's an assistant professor at Northeastern University. Everything good? Everything all good? All right. What excites him is the challenge of designing systems that make probabilistic modeling fast, accessible, and useful for solving everyday reasoning tasks. And broadly, his research focuses on probabilistic programming languages, foundations of probabilistic inference, intractable probabilistic modeling, and automated reasoning and probabilistic verification. We have Armando Solar-Lezama, who is a distinguished professor of computing at the MIT Schwarzman College of Computing. The focus of his research is program synthesis, an exciting research area that lies at the intersection of programming systems and AI. On the one hand, program synthesis is about the use of automated reasoning and learning to help bring more automation to the programming process. On the other hand, he believes code provides a uniquely versatile modeling mechanism, so program synthesis can play a powerful role in helping to build learning systems that are more predictable and robust. And finally, we have Professor Marco Gaboardi, who is an associate professor at Boston University. Marco's research is in programming languages, formal verification, and in differential privacy. His recent work covers topics from linear algebra with tests to frameworks for and models of differential privacy. So just the general format here, I'm going to ask some leading questions, and you can feel free to answer them and diverge a little if you feel like it. So just to start out, if we could go from, I guess, our right to left, to give people an idea of your interest, could you each briefly describe what you find important about PL research?
Yeah. Sure. What I find important about
PL research. Yeah.
Oh, that's yeah, okay.
You can only answer a part of it if you feel like it.
Yeah, it's a big question. No, there's this I didn't start in programming languages, right? So I started in AI. And I think that part of what I found very interesting over time as I kind of drifted more into programming languages was that there were a lot of questions that were being asked in AI that I think programming languages has really interesting answers to. And I'll give you a concrete example. So there's a kind of historical arc in AI around the development of languages for describing probabilistic models, right? So like starting back in the 50s and 60s, we were really into logic in AI, and we had all these really interesting systems for describing large systems of deductive reasoning within logics, right? But the problem is the real world kind of has uncertainty, right? And you often need to unlearn things. And logics are kind of monotonic, right? I keep adding facts to them, and it kind of reduces the number of conclusions that I can draw. Right, so there was this need in AI of kind of adding in probabilistic uncertainty, right, into your system of deductive reasoning in order to get a sort of non-monotonicity. And kind of Yuta Pearl was kind of a pioneer in this idea. He kind of really pushed the idea of adding probability into deductive reasoning. And he came up with this language for describing probability distributions, which he called probabilistic graphical models, right? And that was cool. It was an interesting programming language in some sense, right? But I think there's kind of a continuation of that idea all the way through to making programming languages that describe kind of probability distributions. And I think that's happening today. And I think that that's very interesting because you can start to bring a lot of the ideas from programming languages to this traditional AI idea of representing probabilistic uncertainty. So that to me is very interesting. And it's kind of, I think, still very nascent. And that's kind of what's drawn me more and more and more into that direction of kind of understanding programming languages. So that's my perspective.
Sure. I think programming languages arise out of a very specific need to describe computation very, very precisely and at a scale that had never really been necessary before. And so this gives programming languages this unique ability of describing things to a level of precision that you really can't achieve any other way, especially when you're talking about things as large and as complex as modern software systems, right? And this precision and this ability to describe things so precisely that you can run them on a different chip, different from the one that they were designed for, right? And you can build layers and layers and layers on top of these abstractions that you build without having them break. Today, we're seeing, suddenly we have this explosion of in AI of systems that promise a very different value proposition, where you can define things very informally and in a very flexible way. And at their best, they sometimes feel like they're reading your mind. And but once you start trying to build things of a certain level of complexity and with a certain amount of reliability, you find that pretty quickly, either you fall back on a lot of the ideas that we have from programming languages, or you start reinventing the wheel, trying to figure out ways to corral a lot of these informalities. So I think the world of programming languages and programming languages research has a lot to offer to the world in terms of building on this expertise that we have about dealing with precision and dealing with scale and dealing with complexity. And I find it really exciting that programming languages research is starting to come out of this very specific focus on software development, to really start looking at a lot of problems that are, in some ways have nothing to do with software development, but where a lot of these features can be really, really helpful.
Okay.
Sure. I think, is it on? Yeah.
Yeah.
Yeah. Okay, sorry. I think Steve and Armando already cover pretty well what I would have said, but I can add a few more. I steal also from Shriram. I think that one thing that really characterizes programming languages is abstraction. And I think that all of us like to think about abstraction and try to think about abstraction without forgetting about the formalities or the formalism. So this set a bit programming language aside from other research area in computer science. I think most of our colleagues from other discipline also like to think about abstraction, but not with the same kind of precision that we do. And I think is something that is really valuable, especially when we try to apply programming languages ideas to other areas. For instance, I had this opportunity to work a lot on privacy, which is a community that doesn't do a lot of programming languages, but it was very valuable for me and for the community to see how the programming language approach could bring out some ideas that people already have, but maybe try to clean them up and bring them at a level of abstraction that can be reused and implemented and found more valuable.
Yeah, I mean, I would echo all the points about abstraction. You notice we all keep coming back to the A word. I'll say two things that I think there's something really profound about the distinction between the static and the dynamic. And it's very hard to explore that. Many things don't have that distinction. And in many cases, it's very hard to really probe and really get to the heart of that distinction. And in some sense, this is an old idea, right? If you go back to like Dijkstra talking about structured programming, right? This is so ancient that many of you don't even know there was a time before structured programming. You haven't lived in such an era. But when Dijkstra talks about structured programming, his point he's trying to make is, look, this is really hard. The dynamics are so hard that if we don't even try to get some meaningful alignment between the static and the dynamic, then, we have no hope of making sense of things, right? And being able to do that has enabled us to build these amazing things that, that people here are building and talking about, and being able to apply it in all these areas and being able to use this as a description for other fields. I think it's phenomenal. So I think like that to me is this, we have this unique ability to stand and look at this distinction and talk about, how we can do this interplay and how this sort of over approximation on one side and under approximation on the other side, and we keep playing these games. It's really amazing. When I talk to college students, I say, we can do this. There's this other kind of static analysis we can do called Big O, right? And most sciences would kill to have a static analysis like that, right? If you can do the moral equivalent of something like a Big O for chemistry, you win a Nobel Prize, right? We teach it to freshmen, right? It's kind of amazing that we can do these things and we can play these games going back and forth. And so that gives us this unique viewpoint. But beyond all of this, sure, we can say all these things. I can talk about how useful it is and say all the things we say on the first page of NSF proposals. But to me, at the end of the day, it's just beautiful. And it's fine. It's perfectly fine for us to just want to study and explore beautiful places. And PL is that. That's why I do this.
Thanks for all your responses. So for the next question I have, what ideas from the last 10 years of programming languages do you maybe expect us to start seeing appear in real tools and real programming languages soon?
So we're going in this order, right? So maybe Armando should start.
Sure. I mean, I think we've seen in the last 10 years this explosion in our ability to do program synthesis, right? To the point where, when I started here, I had to work really hard to convince people that synthesizing programs was not just some pipe dream, and that it was possible and that we could actually do it to the point where we could do useful things. And now I have to convince people that it's not a solved problem and that there's actually still some way to go before we can just say, let there be Instagram, and poof, out comes, giant scalable distributed implementation for a web service that allows people to upload their pictures, right? I mean, but I think programming languages themselves have not really sort of incorporated the fact that this ability exists, right? And we're seeing, a very limited flavor of this in a lot of these tools that everybody uses these days, like, Copilot and such. But they really just address one particular dimension of what you can do when you have the ability to generate code. And I do think that we're likely to see much more of the skill incorporated into much more organically into the way we build software.
Who'd like to go next?
Thought we're going round robin.
All right.
Okay.
Sure.
All right. Yes. So I think that something that we will see more and more. Of course, I agree with Armando, but I add another thing. I think is program analysis, in the sense that program analysis, of course, has been studied for 40 years or even more, but hasn't been integrated as much. But I think more and more there is also the approach of trying to integrating these to real programming languages. Of course, maybe program analysis actually is not the best word, but let's say some analysis for the correctness of program. It could be more advanced type system or static analysis or other. There are languages that we know that they are quite well used, that are very powerful. And I think some of the newer language will embrace some of these. For instance, we have seen some of these in Rust with the type system, and I expect this to be more and more the case in the future.
So you set like 10 years, I think, as a sort of weird horizon. I don't know. Yeah.
You can change the
that's fine.
horizon.
No, that's fine. It's fine.
Mhm.
There's enough people here with sort of logic backgrounds. I think there's this, to me, I'm always fascinated by the interplay between proof theory and model theory. And I think we've seen only small amounts of integration of those two things in traditional programming. And, for example, solver-based programming languages are one step in that direction, but I think there's still relatively small steps. And it feels like there's so much more to go. But also, the ability to have oracles of various sorts for our programs, right? And we see this idea come up periodically. You see this idea in solver-rated programming. You're like, let's go out to the solver and ask it to solve something for us. You see that in Ottoman, right? Where let's go out to Mechanical Turk and ask it to solve a question for us. I was having this fun chat with MIT alum, Jeffrey Litt, at some point. And we're talking about the fact that LLMs now serve as this weird kind of oracle, right? You're talking about, imagine Jeffrey always talks about recipes, like the man's got food on his mind all the time. And so, imagine that I want to say like, okay, I've got some recipe and let me fish out all the things that are, vegetables in this recipe. I'm not going to write a regular expression for vegetables, right? But you can ask this oracle to go off and answer questions for you about, like, is this a vegetable or not, right? Or, about pictures, all these kinds of things. And I think we've still not been ambitious enough in like opening up our languages to these really powerful oracles, of which there are many, many kinds. Some are drawn from math, some are drawn from humans, some are drawn from like AI and whatnot. And what would happen if we could really open up the box and really integrate these and maybe even then start to provide guarantees or et cetera, et cetera. So.
Yeah. Predicting change is always hard. It's, I think, there's an old saying about us. Yeah, right. It's like, you always, what is it? You tend to overestimate change in the short term and underestimate change in the long term, right? I mean, I think that, our programming languages are going to change slowly, but over time they're going to look very different, right? So like, I think that, for instance, adding, I think what Shriram said was really interesting with solver-rated programming. We want to add, perhaps sophisticated, like stat solvers as primitives into our languages, right? I think that's cool. I'm a probabilistic programming person. I think you should add probabilities into your programming languages. Maybe that would be cool, right? So like, I think that as programs become easier to write, kind of riffing on the synthesis direction, we're going to be more interested in more interesting languages whose semantics are maybe make it easier to write big programs with small programs, right? I think that that's going to become much more relevant as it gets easier to write programs, and as our program synthesizers become better and better. But who knows? It's really hard to predict. I mean, I still think that we haven't solved, for instance, borrowing in Rust. Like, I'm not convinced that's the final answer there either. So I think that there's lots of little things and maybe some big things, and it'll be interesting to see where things go.
Right. So as has already been brought up, machine learning and language models have been increasingly seeing application across computer science. What elements of our field do you expect to be the most affected by these tools? And what elements do you think are going to stay the same? Want to go, Marco?
All right. So I think that one that will be affected the most, I think, is the one that Armando mentioned before, program synthesis, and code generation is for sure something that will be affected a lot. I think that part of the question is part of trying to figure out how to use it in the best way is also trying to figure out what correctness we want from our code or what requirement we want the code to have. But there are great people that are working on this problem. So I expect that there will be a fruitful integration there. I think another integration that we have already started to see, it has already been studied for 15, 20 years or even more actually, is in coming up with proofs and help with proving. So part of our community also focus on verification, and there I think also this kind of technique can definitely help. What will remain the same is another prediction that is difficult to say. I think that actually the community overall will try to enlarge a bit the interpretation of what a programming language research is to account for some of these questions that the use of machine learning bring to our community. So I don't think very much will remain the same. But of course, the approach maybe is what will remain a bit the same. We will still strive for a good abstraction and precision.
So I'm totally not qualified to comment. I don't know, but let me throw out a challenge that I think we might finally be able to make some progress on. It's a thing that's bothered me for a long time. Starting in about 2009 or so, I started to work on building semantics for a whole bunch of like real world systems as they are in nature. Okay, so everything from JavaScript and Python to like Cisco routers, but not like, you know, the Lambda calculus right in a Popple paper, but the thing that actually is out there, right? And this is a Herculean task, extremely painful, extremely like not fun. Okay. There's actually a part of it that is fun that requires the expertise of a semanticist. And then there's a whole bunch of unfun parts that you usually ignore in the paper, but we actually went through and found not to be fun. And, you know, this is a thing that I think is really right. And the reason it matters is if we want to be able to say anything about our software stacks, one alternative is you rebuild the entire software stack from scratch in completely formalized ways. And there are people at MIT and various places that are trying to do that. The other is we try to actually bring semantics to the things that we're actually running things on and try to make sense out of them and try to be able to talk about verification up this 10, 15 layer tall stack that we're all sitting on, right? And I think there's a lot of promise for doing that with data-driven methods and AI-based methods. We actually crystallized this into a challenge paper several years ago. We called it the, you know, obviously it has to be the next 700. It was the next 700 semantics was what was the paper. And the paper was actually like, it's one of my favorite papers because there's 3 different things that we tried that failed. And we said, here are all the things we've tried that failed. We don't know how to do any better, but here's this challenge we'd like other people to work on. In fact, Armando made a little bit of progress on that using some synthesis methods. But I think it's still a wide open problem. And if we can bring, and the thing is, again, using the static dynamic relationship I taught, we have the source code to these things. We can run these things. We can get, you know, traces of these things, all these things. If we can use these methods, these data-driven methods to obtain semantics, now we've moved all these like wide open, messy, ugly systems problems into a realm we have a lot to contribute. So.
Yeah, that's yeah, that reminds me of something interesting that we've been thinking about, which is, you know, not necessarily looking at real world systems per se, which is a very fruitful place to look for interesting semantics questions, but actually looking at old math and like thinking about like you know, you tend to look at old math books and think like, oh, these are solved problems. Like this is the right way to approach, for instance, probability. And I'm starting to think that we kind of just have probability wrong, and it's sort of disturbing. Like for instance, you know, there's lots of basic things that you have in a probability textbook. If you go crack open a probability textbook and look at the exercises, and they'll have things like, well, this happens and then this happens, and then they'll make a decision and then they'll do that, and they'll describe a sequential process. Maybe it has a loop, for example, in it. And then you're like, oh, well, what is the semantics of that? Right? Like, what are the implications of this process that they're describing to me? Like, is this something that's allowed to be spoken in my language? Is a very serious question you start to ask. And especially when you get into interesting probability, like stochastic processes and things like that. You're like, ooh, I have an infinite set of decisions. And ooh, then there's like an infinite loop that almost you know, does that terminate? You know, so you start to get into these questions, and then suddenly your PL brain turns on. You're like, wait, you know, like, is this a Scott continuous function? Like, is there actually a semantic domain that I can get to this thing? And, you know, like before you know it, you start to have a whole different vocabulary for asking these kinds of questions. And you start to think, can I rewrite this probability book using much better language? And I think that's actually a very fruitful thing that can happen, and more than just probability. I think there's actually lots of mathematics where you can go and look for that kind of thing. So I think that's a fun place to look, actually.
You also have to call it structure and interpretation.
Yeah. Sorry, yeah.
The next time on structure interpretation. Not of all the beams.
Yeah, I think one of the, you know, if you look at the PL literature, right, there's all these really cool things that we can do that suddenly when you are actually sitting down and writing real code for some real problem that you have to solve, you kind of feel like you're living in prehistory relative to the sort of tools that you could have if somebody had actually gone and built all the things that people talk about in research papers, right? And, you know, some of it is, well, things are harder than they look when you try to apply them to real problems, and it requires lots of research to actually uncover those problems. But some of it is, we haven't even gotten to those problems because it's just so incredibly painful. And not only that, you go and you build your super tool for, you know, Rust, right? And then you realize that Rust is like this little sliver of the you know, programming languages landscape, and it's nothing against Rust. It turns out that any language that you pick is just going to be this tiny sliver of the full programming languages landscape, right? And then you build this tool for this one version of this one language, and you realize that first of all you have to do all these work so that it actually deals with all these libraries and all these black box functions that are implemented in native code. And then once you do that, then the new version of the language comes out that changes everything, and suddenly your tool is not compatible anymore. So these are the sorts of things where I think there is a lot of potential for sort of this meta automation of automating the automation and allowing you to really deal with the challenges of scaling up, and both horizontally and vertically, all of these different things that on a theoretical level we kind of know how to do. And even for the things that we think we know how to do, to actually run into the problems that we haven't even gotten around to running into because it's just too difficult and too painful to run our tools at scale.
All right. For a slightly different direction, at least for those people on the panel who can think of themselves as having changed research subfields or focuses at some point during their career, could you comment on what led you to prioritize a new direction or a new focus? Could you comment? Yeah, could you comment on what led you to prioritize your new direction or new focus? See how we got Shriram?
I mean, okay, I think for me, it's very simple. When other people start working in a field, I move out. Because I just figure, like, I don't know that I'm some sort of genius, that I'm the only one who can solve it. And if other people have gotten excited about it and are interested, then I'll solve the problems. And, you know, yeah, I actually, yeah, I'm going to give a very sociological answer. I hate waking up in the morning worrying about whether like somebody else has published a paper that I'm trying to work on. I don't want to have to check archive every day. Like, this is just not how I want to spend my life. So it's all part of the same thing. Yeah. And there's enough exciting things in the world. There are enough like hard problems to solve that usually I like to work on a problem for about 5 to 7 years. It takes about 2 to 3 years to get up to speed, and then about 2 to 3 years to like really make a contribution. And then like, you know, 1 or 2 years at the back end, like you publish it and like clean it up and really understand what you did. Like while you're in the thick of it, it's hard to understand what you're doing. And then you look back and you say, oh, that's the actual principle. That's the actual thing. And then you sort of crystallize it into 1 or 2 papers. And then, you know, other people start paying attention, and then you're ready to find a hard problem. Not a great answer, but it's.
Thank you.
Sure, yeah, I can comment. Yeah, I mean, I think I'm the newest one here, so I've had the least time to change, I suppose. Yeah, you know, so I think that definitely one thing I like to be is a little uncomfortable, right? Like I like to feel like I'm somewhere I don't know everything, right? Because I feel like then I can bring the stuff that I know to this relatively uncomfortable place and kind of grow and be excited and learn new things. So, you know, I definitely like to, you know, put myself in a situation where I don't necessarily know everything so that I can learn. And I think that's really exciting. I also think that it's hard to really appreciate something unless you came from somewhere else, right? Like if you just grew up in the world, you know, like it's just everything you know, and it just feels like it's the way the world is, the way it should be. Right. And I think it's a lot harder to appreciate that when you've grown up in it. Right. There's this classic kind of polemic from David Mumford called The Dawning of the Age of Stochasticity. Oh, you know it. Great. Yeah. So he has this phrase in there, which I love, which is like the zeal of a convert. right? Like that's how he opens. He's like, you know, like I love probability now. I have like the zeal of a convert for probability. And I feel like the people who are most excited about something are the people that came into it later after having experienced something else to have that perspective. So I think that that's something that is nice when you move into someplace new. You really have that kind of new perspective on it. And I think that makes it much more exciting to kind of work on that stuff. Yeah.
One of the things that I really like about working in PL is that it is precisely this toolkit that is really valuable and useful in lots of other domains, but in a way that many people don't really appreciate. I don't think everybody kind of knows that, yeah, machine learning is kind of useful and you can use it for lots of things and in lots of places. I don't think people have quite the same sense of PL. And so it has been actually really nice to be able to go and jump into different fields and look at problems in different fields and come in with this attitude of, well, I don't know this field. I'm going to have to learn a lot. And you can't just come in and say, well, get aside because I have the truth here. And so, you bozos need to just listen to me. But I think it's, we do have something very valuable to offer. And it's always really fun to go into a field where you don't quite know the issues, and you just have to accept that it's going to take you a little bit to go and or sometimes more than a little bit to go and understand what the issues are. But it's to me it's kind of the most fun way to do research. It gives you this opportunity to be learning something different in every new project that you run into, but at the same time you're not just coming in as a tourist, right? You have something, you have a certain commitment to actually learn the field, and you have a set of tools that you're contributing that hopefully will make the field better.
Answering this at the end is more challenging, but I think that I just rephrase what others have said. Like one thing that I think as a researcher we fight against all the time is being bored. So we need something new all the time, and that's what brings us to research. And so I think a part of the reason why I look I had the changes in my past and in my research was because I felt like I understood a problem. Maybe I understood an area. Let's say I could keep working on that forever, but I feel like now it's time to move on and try to understand something new. So I think that's a common way. I saw this in many colleagues in computer science and more in general in research. So fighting a bit the boredness, I guess, is what brought to changes.
Do you mind if I add one more thing?
Sure, go for it.
It's sort of related to some of the lunchtime conversations we had. I had this experience of this is partly I just want to warn, especially the grad students here, like this is a way like academia will fuck with your brain. Okay, I had this experience the first time I went to actually it was I think SIGCHI I went to, right? And I walked in and I remember thinking like, holy shit, I am the lowest status person in this building. I knew nobody. I'd go to PL conferences and all these sweet grad students would come and try to tell me about their work and feel really good, right? Your ego is inflated. We all know what that's like, right? I go here, nobody wants to talk to me. In fact, I was kind of lower status than the undergrads because even the undergrads belonged to somebody's research group, right? So they had some tribal affiliation. I'm so-and-so student, right? And I was nobody. And I remember the first 5 seconds, geez, what's going on? And I thought, and that is a very important moment because one of two things happens, right? You either flee to safety or you say, oh, wow, this is cool again. It's exactly what Steve was saying about being uncomfortable, right? You're seeing this, you'll see this echoed. And you need to understand, academia is really good at building up all these status symbols and giving you all these little dings and dongs. And so you have all this status and you have to be willing to walk away from that status when you move to a new area. And I think everybody at this panel has had that experience of like having to walk away and start again. And it's actually super exciting. It's exactly like being a grad student all over again. Remember how exciting that was when you started grad school? It's like that, but you have a real salary, right? It's actually okay. It's actually okay, but you just have to like let those first 10 seconds pass. Just keep that in mind, because everybody here, like someday you'll have this experience. I hope like you'll remember and say like, oh, it looks like it worked out okay for sure. So maybe it'll work out. Just power through it.
So tying into Armando and Shriram's comments, what are some concretely some new areas that you think people in the audience should consider trying to apply their programming language knowledge to? You know, areas outside our field that they should look into.
I have to follow where's a new place to apply programming languages to? I mean, I want to give you one that's not mine. Something fresh. I mean, so I think that there's, there's a whole world of people that work in scientific computing. They work on things called codes. They don't even call them programs. They call them codes. I think there are people here who work with people who call programs codes, actually. So so we've got some codes. But I think that there's, and maybe then you guys have heard about this, I don't know, but if you haven't, great. So there's a whole group of people that do not know about the kind of programming language research that we do and write some very large and very important programs, right? Like these are the programs that people use to make very important decisions about stuff like climate models and weather models and things that are extremely important and really affect us every day. And I think that these are places that I see as very ripe for programming language solutions to their problems. It's just really, really hard to make these systems. They're really large, they're very complicated. And it's very hard to break into that. You have to really know deeply the area in order to talk to those people. So I think that's an interesting area I would try to look at, just because I think they have very unique problems in that space, and they're open to solutions, right? So like I've talked to people at those high performance computing conferences and told them about formal methods and verified numerics and things like that, and they're like, that is exactly what I want. How do I have that? So like I think there's appetite, but it's the kind of thing where you really have to dig in. I think that's something that's really important with this kind of exercise is you have to really dig in and talk to people. I think one of the worst things you can do is get a shallow understanding of someone's area and give a solution to something that's not their problem. Like that's bad. You really want to understand what their problems are, I think, if you're going to do that.
Yeah, I think there's lots of really exciting areas. One that I'm really excited about these days, for example, is in computational biology in general. I think as a warning, there's lots of dead bodies of people who have tried to go into some of these areas, and I think underestimating the level of engagement and the level of commitment that you need to really get to the point where you understand what are the problems that people in that space actually need solving, and to really understand that it's not just going to be getting there and taking your tools and now your tools will work and solve the problem, but rather using your the skills that you've developed to go and come up with new solutions to their problems that are informed by everything you know and everything you've studied, but they're not just your technique applied to the new problem. I think there's a lot of opportunities these days in, for example, around social sciences, where there is a big need for techniques that are able to turn data into models or data into insights, but they can't just have the kind of black box models that machine learning is able to provide them. And they also can't have the massive volumes of data that high-end machine learning requires. And so really what they need is something that feels a lot more like program synthesis, right? And turns out it's something that we actually know how to do. But again, I think it is very important to come in with a very open mind, ideally with a partner that actually really understands the domain and who is also willing to put the effort into bridging that gap, because there is a gap, and it is going to take some work to bridge it.
Thank you.
Right. I want to mention two, actually. One is a bit more clear. The application, I think, is that area that we often call econ CS. So there is a lot of work between economics and computer science. And I think a programming language researcher haven't looked too much into this area. There are few works, but I think that there is an opportunity for much more. Now, the second one, I want to spend a little more time because I think is a bit more controversial. I think is education. I think that, and I'm talking about education both at the children level and middle school level and higher education. I think that the way programming language researcher, this is a way of thinking about abstraction, but at the same time talking about precisely some behavior, I think is a very valuable approach to also how we could approach education. And I had some experience, I'm sure Shriram has many more, because he has been working on computer science education, but I think besides computer science education, more in general, education can benefit from our way of reasoning. I had some opportunity to talk with people that study education, so our colleagues that are in the College of Education. And I think that there is a potential really for some bidirectional work in the sense of bringing some of their thinking to our setting and bringing our thinking to their setting. And it's not only, I'm not talking about really technology, I'm talking about a way of thinking. And I think that could be really useful. We have seen some of it when there was the computational thinking slogan brought to all kind of education, and I think we can see it more.
So as I've worked in several sort of CSX things, I don't know that I have anything to add to what people have said here in the sense of how to approach it, but I'll actually say something. Let me say something to scandalize people here a little bit, because I think it's actually very important. And it's because it's a thing I've learned I have to say over and over to people who come to me and say, hey, you worked on X, can you help me figure out how to do, bring PL, they're always PL people who come to me and say, and the answer is always, the polite version is nobody cares about your programming language. The actual version I say is nobody cares about your fucking programming language. Okay. And I'm serious. Like, I think it's kind of important to understand this, right? People in an area want to solve a problem. They are not steeped in our brilliant ideas of beauty and devotion to all these abstractions and so on, right? I mean, in some sense, like you can go talk to scientific computing people, but at the end of the day, they're like, you can have it in any color you want so long as it's Fortran 77, right? Like they're not about to rewrite everything in Haskell and switch from arrays to like, whatever version arrays and purely functional, whatever. And they should, of course they should. Someone's wrong about that. But the point is they're not going to, not in the next 20 years, right? And if you approach it as you are fundamentally wrong, and let me tell you what is wrong with you, guess what? It turns out humans are not so great at responding positively to that, right? And I rarely met a branch of CS that is quite as convinced about its rectitude as PL. And I mean, there's a reason for it. We're right, of course. You can't tell people that. Okay, and this happens all the time to me in education, right? People are like, hey, Shriram, you've been doing like CS outreach 15 years very successfully. I've got this awesome thing in Haskell. It's like, okay, but it is awesome, but what do you understand about the day-to-day needs of schools? Well, I mean, I'm sure they would benefit. In the moment you say, I'm sure that, it's like, probably not. Okay. So yes, you can form collaborations. You're going to be most successful if you can either find a deeply sympathetic collaborator, or if you actually immerse yourself, right? But if you walk in with like, okay, PL is going to solve your problems, even though it may be true, you won't have the impact. Right. And you have to decide whether your goal is to be like, to win a moral victory, or which is fine, I'm totally, look, I'm a functional programmer at heart. Of course, we're all about moral victories, right? That's all we have to show for the most part. So I'm fine with that, right? But you have to decide what your goal is. Is it to have like widespread impact? How much are you willing to compromise? These are all questions you have to ask yourself. And they're like tough questions you have to ask yourself. And if you do, you'll know what it's like writing down a test case before you write your implementation, right? Like, or writing a spec before you write your implementation. Understand where you stand, and that'll help you as you have these conversations and as you navigate this space.
A slightly more specific one. Programming languages have traditionally relied wholly on textual interfaces. Earlier, we had a talk on interactive user interfaces in Lean 4, for example, with visual or other types of interfaces. Do you see any opportunities in the areas you work in to employ visual or interactive interfaces as a part of programming language work?
Yes, absolutely. I think we text is great, and it has a lot of things going for it, but it's not particularly natural for a lot of things that we really want to do. And there are some domains that are just by nature very visual, and where that just has to be part of the interaction mechanism. But even domains where that is not the case, we are very visual creatures, right? And so just unilaterally deciding that no, that's not going to be part of the picture, I think is really putting us at a disadvantage. And I think there's all sorts of historical reasons why text has been the default, and why things that have tried to rely on things other than text have really had a hard time coping. But I do think that this is a really important direction.
Let me see what I can add. I guess that we are already lucky that we don't work with a 0-1 string. Right? There are some of our colleagues that do that. We do at least use languages, so we are a step up. Now, of course, I agree that it can be very useful to think about other level of abstraction.
I'm going to give a more nuanced answer here. I think there is a computer scientists suffer from this images are good fallacy, or images are easier fallacy. And as somebody who spent the past about 5 years really understanding the cognitive science literature, I think once you actually study the literature, you realize how much more complicated this question is, how much harder it is to reason visually, what the affordances are, what the strengths, weaknesses are. So I'm not going to give you like a blanket answer. Like obviously, like text, all text only is obviously bad. Multiple channels, encoding, cognitive encoding, et cetera, et cetera. In fact, like it's too bad Will's not here, because Will and I would like rant about this for hours about this. But let me just say the following thing. Here's a really valuable software engineering. Is he waving there? Yeah. Good job, Will. Thank you. So here's a really valuable software. Is he doing it again? So here's a really valuable software engineering principle, right? We all know, recognize, and love model view controller. Okay. Our programming languages are views, but we treat them as models, right? Why do we not have multi-modeled ways? And like, think about what we, like one of the oldest things in computer science is what we call the syntax war. We don't call it syntax discussion. We don't call it the syntax appreciation day. No, we call it the syntax war, right? And what is syntax? It's a view over a model, right? There's an easy way to resolve the syntax war. It's called model view distinctions. Right. And there's a handful of things that people have done. I, amongst other people, have built like block interfaces in addition to textual interfaces for the same language. It's a complicated, messy question. And yet somehow we have not applied a foundational software engineering principle to the foundational tool for software engineering. Like, it's just so weird. right? So I think there is actually this much richer space to be thinking about. And I'm going to say that your question's a tiny fragment of that, but be careful about the computer scientist fallacy about like visual stuff. We're full of fallacies about this.
Yeah, this is an interesting question because I think that, maybe not with images for me. I don't know. I haven't thought too much about images, but what I've thought about a lot about is programs that have very weird semantics, in particular, maybe probabilistic, maybe quantum, programs whose runtimes are not von Neumann architectures executing one instruction at a time, right? How do we help programmers understand what those programs are doing so that they can debug them or interact with them in interesting ways? Like, for instance, I think it'd be really cool to make a programming language for teaching elementary schoolers probability, right? And like, it would be very interesting to observe someone, of that age using a program and seeing the questions that they are asking as they're using it, right? And I think they're not going to be things like, does this get here? Like, or like, what happens if I do that? It'll be like, how often does this? Or, like, if I do this, will this become more blank, and like these kinds of questions. And so like, our interfaces have no such affordances, right? Like, we can't ask those kinds of questions. So you need an entirely different interaction modality with these kinds of systems. So yeah, I think that as our languages become non-standard, right? And like, it's interesting too, like, I've always thought that the user interface for logic programming languages was horrible because I can't see the proof tree. So, like we haven't gotten that one right. So it'd be pretty useful to get that one right. So anyway, I think there's a lot of room there, and I think everyone agrees. So my only question is, why haven't we done it?
Maybe just to say a last word here towards the why haven't we done it? I think it is important to think deeply about the why haven't we done it, because it's not just that we haven't thought of it, right? Scalability is, for example, a really big issue the moment you start talking about visual
Program in
things. Scratch
for 10 minutes and you'll run into half the problem.
Yeah. It's really challenging to scale. I think there is something very powerful about just having this very simple, uniform format that doesn't require very sophisticated tooling to work with. And so I think thinking about some of these restrictions is useful. You don't want to just trip with the same stone that people have been tripping with for many years.
So as we're sort of getting towards the end of the panel, for the students and others in the audience who are maybe sort of just getting into PL, what is a key point you think they should take away from this panel and or the larger, programming language review today?
It's the easy. From the panel, I'm not sure.
Look, okay.
Except that they should talk with Shriram and ask him about PL plus X and how to deal with that.
No, look, listen. You people have no idea how awesome this is, okay? Like I am the second oldest person in this room, okay? And when I was in grad school, when I started grad school, some of you may have heard me say this before, I'll say it again. When I started grad school, I was told there is no point studying programming languages. It is a dead field. Okay, we have C++. C++ is both high level and low level at the same time. It's a solved problem. It is a quote unquote multi-paradigm language. What on earth is left for you to solve? Okay, and the answer turned out was C++. The answer. Okay, so you can't even, like, I had to like fight with argue with people who would say this like with a straight face. They meant it. They were trying to save my soul. Okay, and as I was saying at lunch, I actually started in comp bio and I switched to PL. People are like, what are you doing, man? Right? So it's like, the thing you should take away is that PL is as wide open as ever. It is as optimistic a field as ever, okay? And it is as applied as ever, and at the same time as foundational as ever. We've seen some really cool foundational stuff. We've seen some really neat stuff that makes the foundational stuff much more accessible. We've also seen some really cool applied stuff, right? We've seen everything from like, compiler optimizations to proof mechanisms to higher level programming languages. It's all here, right? In fact, this is a very cool collection of papers and it's great, but There's, I'd say, a whole bunch of CS that hasn't even been represented today, and that is not a criticism. It just says how mind-bogglingly amazing the field is right now, right? So what you should take away is like all of this, it's great, it's awesome, and you don't have, and if somebody says C++ now, you can afford to laugh at them. So it's, yeah.
Follow that? I mean, it's, you know,
I mean, you disagree?
no, this is great. What more, what a positive note to end on. No, you know, I think that there's, it's hard to put a finger on like why one particular takeaway. I don't know, this is very difficult. I think that, you know, there are several strains in this discussion that I think are interesting and that we should definitely think about. And one in particular, I think, is programming is going to change, right? I think that a lot of people know that, but haven't internalized it, right? Like the way that we teach programming is going to change, right? In particular, it's going to become a lot easier to write programs than it was. The kinds of programs we're going to write look very different. That might be taught to much younger people, right? And I think that, you know, you have to not become too attached to C++, because, you know, there's a good chance that that's, you know, still going to be here, but I think we need new ideas still, right? And that's kind of, maybe I'll try to guess that that's something that's worth thinking about.
Yeah, I think, you know, to follow that, I think rumors about the death of PL have been greatly exaggerated. I think hopefully the takeaway you get from today is just about the liveliness of the field, but I think we're really just getting started. I think, you know, a lot of the forces that, you know, some people might think are going to make programming and programming languages less relevant are actually pushing very much in the opposite direction, right? In that, for example, a lot of the things that used to make adoption of new programming languages difficult, such as the difficulty of building up infrastructure for them, the difficulty of translating legacy code into them, the difficulty of creating even learning materials for them, right? A lot of those things are things that we can actually automate away, right? And now we have this whole new dimension of systems that are very, very powerful, but we actually have to figure out how to program them, right? And how to actually harness them to do the things that we want them to do. And this is what programming is all about. It's finding new ways of getting systems to do what you want them to do and describe a lot of complexity in very expressive ways. And so I think, if anything, we are actually about to get into a stage where there's going to be huge opportunities in PL. And we need a lot of PL researchers to take
But the
advantage
new
of it.
golden age, we should just adopt the term and then it'll come true. Yeah.
I never actually heard about the death of PL. Otherwise, I would have changed.
All right, well, if you
I can add something else about what you can take from the panel today. That I think PL, as we said, you have interaction with many people, and what you should learn from us is to be humble in those interactions. It was meant to be a joke.
Took it seriously.
No, but seriously, I think being, especially in the interaction with other people from other areas, is important not to go in thinking, oh, I have all the solution. The solution will only come from the interaction. There is no way we come in with the solution, and to gain the best from the interaction and humble approach, I think, is the best, because there is a lot to learn from people from other areas.
well, do you have something you want to add?
Actually, I have a question. Could the people who organize please stand up?
I guess whoever's on the committee who's here right now. Thank you very much to our panel who took some of their weekend to come out here. So I appreciate you all being here.